we have come to our last day of class. I know, such sadness. So we want to talk a little bit about preconditioners. Right? We've actually given a little bit of a tip of the hat towards this earlier on, particularly with eigenvalues and that. But I want you to think about what might make a reasonable preconditioner on these things. And we'll start off thinking about the problem AX equals B. And there's a pretty natural extension of this to when you're dealing with eigenvalue problems. But for something to be a preconditioner, there's kind of a double use of pre in this sense. One of which is that we do it before we do our iteration, we just run it on a slightly different system. But we're also going to pre-multiply. So imagine I have some matrix M that I pick. So I'm going to take M inverse, and we'll explain why M inverse in a sec here. And I'm going to multiply it on the left to both sides of this, so I keep them the same. Now, as long as my original M is such that it has an inverse, i.e. it's full rank and things like that, then mathematically this problem has the exact same solution as that problem does. As long as it's full rank, it may move things around a little bit on the column, but it's not going to change anything over here. Right? So these two, by their very definition, have to have the same solution. As long as M is full rank, which is why M inverse would exist. So then the question is, well, what benefit do I get from it? Well, in pure mathematics, in infinite precision, you gain nothing. Right? That's just reality. However, in finite precision, where we have to approximate things, you gain a lot. As long as you pick the right M inverse. So the challenge is going to be kind of twofold. When we move to this, I have to do kind of two things. I have to apply the M inverse. And then after I apply the M inverse, I'm going to have to do whatever my solver is. Okay? So I might have to do kind of two steps. So I want each of those two steps to become really, really fast. Okay? So for instance, applying the M inverse, if M itself was a dense matrix, then I'm stuck doing basically M cubed if it's an M by M matrix. Right? I'm stuck doing just a huge amount of calculations. So this would be very, very inefficient. So in order for this to be efficient, to calculate M inverse and apply it, and in truth we usually do this by backslash, unless we get the nicest of all things to calculate inverses on. If I could say you have to calculate an inverse of a matrix, but you get to pick the matrix, right? What would you pick that matrix to be as a type? So identity is a really easy matrix, right? Its inverse is itself. Okay? Now, is there any challenge though with that one? Does it, if you applied identity here, would that help anything? Right? You get the original problem back. So identity is very fast and easy, but it can't do anything for me. Right? So, but maybe that can give us a hint at what things might be really easy to calculate.
What is that if you multiply by its inverse together?
By its transpose. So orthogonal matrices or unitary. Remember, that's for reals and this is for complex. It's the only difference, right? Both of these, right? M inverse equals M, I'm just going to say star, conjugate transpose, because it covers both. If it's real, that conjugate transpose reduces. Okay. That's fairly easy to do, right? So this is one category of things that's fairly reasonable to go on. Now, right, if I were to apply one of those to here, what would happen? if I take an orthogonal matrix and apply it, what have I done? What was yours, and then I'll get yours. Okay, so I'm kind of rotating the problem, right? To try to align them on some easier dimension.
Similarity transform.
It is, it'll be a similarity transform if I do something on the inside here, right? But I gotta do it to both sides. Now, I can do that, right? And this is how we get into the eigenvalue one, as long as you mention it, I'll put her in. I want M inverse A times something here. Well, if I wanna keep it on M, then M inverse A M would work, but if I have the M in here, that would kind of mess things up, right? But what if I did that? M inverse is identity, right? So remember, most tricks in mathematics breaks down to multiplication by 1, right? Or addition of 0. So here you go, addition, this is a multiplication by 1, I just stick an identity in there. And then I say that identity is MM inverse. In which case, I can get exactly your similarity transform and it stays the same. M inverse X. And this is now a similar matrix. And then we usually just call this Z when you solve for it. And then you've got the solution M inverse X equals Z. And you solve that to get your X. Right? Which in this case, the inverse of that was just going back to the original M if it's an orthogonal situation. So this can give me some things on here, but all of them do exactly what was stated. They're just going to do some rotation or reflection. They're going to kind of twist them to try to get things so that the individual ones are more independent of each other. That's what we're trying to get to. Right? Does that change the conditioning of the problem? No, if I multiply by an orthogonal, possibly even on the left and the right to do similarity stuff, does that change the conditioning of the problem? And no, it doesn't, right? It'll make it easier to solve, right? If you do it correctly, they're gonna move more independent because they're gonna become more diagonal. And diagonal problems are easier to solve because there's no cross coupling, right? So it will make your problems more independent, but it's not going to change the conditioning. What does conditioning depend on?
How distinct the eigenvalues are.
Yeah, so we look at the spread of either the eigenvalues or the singular values, right? Either of those two, depending on the type of problem, one of those two is the thing that we'll talk about what makes something ill-conditioned. The condition number specifically refers to singular values, but in general, conditioning of your problem is which one's more important to you, right? The spread of singular values, the spread of eigenvalues. So for instance, the eigenvalue ones is often associated with what's called stiffness, right? If you have a really big and really small eigenvalues, it turns out almost all numerical solvers have a huge problem with this. And they say that the matrix is very stiff. And what they mean by that is if you've ever taken, like you take a cooked spaghetti noodle and they bend and they flex and everything else. If you take a dry spaghetti noodle and you bend it, what happens? It snaps, right? But it's going fine, fine, fine right up until it snaps, and then it snaps really nasty, doesn't it? Right? It doesn't just break in one spot, it usually breaks in multiple spots and all kinds of fun stuff like this. And because the dry spaghetti noodle is very stiff, right? So when it's stiff, it gets to a certain point, and then when it breaks, kind of all hell breaks loose, right? So stiff things just don't respond well to those forces. They react nice only up to a point, and then it's just all over with. Whereas more flexible things, like the cooked noodle, will bend with things and you don't have a problem. So in analogy to that, we say that if the eigenvalue range, right, includes very large and very small ones, then we say it's gonna be a very stiff matrix for solving things. It'll tend to give you, you know, a lot of difficulty. You'll have to keep reducing the step size smaller and smaller, so that as you're solving these things, taking little guesses to get to the next point, even when it looks like it's smooth. And if you do anything larger, it'll break. And if you go too small, you'll have to take so many steps, it'll break. So no matter what you do, you're pretty much doomed, right? So that's another example of the same type of phenomena. Eigenvalue spread causes stiffness, which is an ill condition of the problem. Right? So if I want to get rid of that type of a problem, this won't help me. This will help you in a lot of cases, but what it's going to do is it's going to separate things. It's going to parallelize them. It's going to make them independent so you don't get as much of a buildup between them. But that doesn't mean that it's going to make the problem better conditioned. It's just going to make them more independent. Now, that might remove some of that problem if there's no buildup between them, but it might not. Okay? So, orthogonality has its use, but it won't recondition me. Any other thing I can do that's got a really easy way to solve things? Diagonal matrices. So, if my original one is M1, M2, all the way down to M up to, say, element N, and it's 0 off, right? The inverse of that is 1 over M1, 1 over M2, down to 1 over Mn. Inverse for diagonal matrices are stupidly easy to calculate. You just invert the diagonal. Leave the rest of the thing 0. That's pretty nice. So that's easy to calculate. Will it scale things? I.e., if I were to put it into this equation, and I multiplied the diagonal by here by 1 over M1, is that going to rescale stuff? Could it change the condition number? Yeah, it can. Right? What's that?
If I'm multiplying by the inverse, and that'll make it stronger as long as that is above.
Right, so now the question is, why do we do this? And I said we'll get into why we're going to do the inverse in a sec here. But we're multiplying basically by this one. Okay? Now, let me show you why we picked this particular thing for M inverse. If I picked M to be the identity, this is just the original problem, right? What if I pick M inverse, or pick M to be equal to A? Okay? Now, ignore this for one sec. I'd have A inverse times A inverse B. Right? If I had a good way of doing that, this just goes away, and I've got my answer X. There's like no work here. Right? It makes this step basically nothing. The problem is converting from here to here has all the work of the original problem. So I don't save anything because I shoved all the work here, right? And then the last step is like, look, X is equal to the answer of what you just calculated. But if you notice, I'm leveraging work between these two sides. How much is done here, how much is done here? What if I pick M to be something like the square root of A? Right? Something close to it, right? Just as an idea on the first cut, okay? Well, calculating that if I've got a reasonable structure, or I pick a reasonable structure to make me look kind of like the square root of A. I'm not going to require an exact square root of A, but if it was kind of like the square root of A, like for instance, if I'm solving AX equals B, and I got some idea about the eigenvalues, I can pretty quickly get the biggest and the smallest eigenvalues, for instance, and I can interpolate between them, right? So if I did something like that to quickly get m, and I just took the square root of the largest eigenvalue and the smallest, m would be diagonal, so this step would be very fast. Do we agree? How about m inverse times the a? What would that do? Well, m inverse times the a is going to scale each of your rows slightly differently. And each eigenvalue is associated with a different row. So I'm applying different scalings. And my scalings will be running from the largest to the smallest eigenvalue. Right? And a kind of linear interpolation of them. But about the square root, which means my condition number will now go, or my eigenvalues of this new matrix are going to run basically from the square root of the biggest to the square root of the smallest, which means they just all got pulled towards 1. Right? Because if you take a square root of something small, it moves towards 1. You take a square root of the bigger things, they move towards 1. Square root always moves you towards 1. It's kind of the fixed point in that situation. Huh? Now, if my eigenvalues are close to 1, how does that work for most of my iterations? Conjugate gradients, GM-res, Lanczos, Arnoldi, our big 4. Do they like eigenvalues near 1? Yeah, for all of them, that's the condition for fastest convergence. The closer, the more they cluster those eigenvalues around 1, the better you are for whatever iteration. Now, there'll be a nearby thing. If it clusters towards any non-zero value, it'll usually do fairly well too. But like 1 is the primo of primos. Okay? So I can get nearby as long as I pick these even somewhat close. If I'm clustering near 1, that's great. I can shift it to someplace off 1 if I'm trying to keep some things away from 0. But overall, if I can make the eigenvalues of this go near 1, or commensurately this if I'm trying to do a true symmetric, then I'm in a great spot. Does that make sense? Now, very often, we won't do exactly this. We'll actually do something a little different. We'll do minus star and m star. All right? Now, the variant on this one is, if it's a diagonal matrix, it actually doesn't matter, right? Whether I do the star or not, because diagonal matrices, star just is going to transpose it. Diagonal transpose is just itself. Right? But if you allow some orthogonality, you're trying to reduce the area, or if you're trying to do some separation, you're trying to split off two sides of the problem where the eigenvalues are big and small or whatever into little subsections to deal with. Often we want to multiply by 1 and then its conjugate on the other side to preserve things. So that often comes into play. So we'll often deal with this type of a setup. So generically, we typically will see problems written this way, m star, minus star. And all this means is take the conjugate and inverse, and then invert it. Or you could do it the other way around. You could invert it and then take the conjugate. It will do the same either way. So you either take the conjugate transpose and then invert, or invert then take the conjugate transpose. So, all right. Reasonable? So the whole goal of this thing is we're just picking some scaling. Think of these as scalings. And you want to pick them in a fast, easy way that's going to make your conditioning of your problem, either the spread of the eigenvalues or the spread of the singular values. And singular values only really matter in GMRes. Right? It's the only one that worries about that. So for everybody else, you care about the eigenvalues. And as long as we can get those eigenvalues close to 1, or clustered near 1, or clustered near some non-zero number, then convergence of those algorithms will go much, much faster. So that's the goal. And you want to pick an M that makes your life easy. So some common choices, like I said, you know, picking a diagonal, find large and small eigenvalues and get a spread of them. Right? So that's one reasonable way you can do these. Another one is what's called the Cholesky factorization. You know, I'm up with tilde eigenvalues as option 1, right? Meaning approximately the eigenvalues. We often use that, like double 1 would be approximately equal. Right? So something around the eigenvalues. A second one that we'll often do is the square root or the LU factorization or the Cholesky factorization of A. If the A is symmetric, the LU becomes Cholesky because L and U become the transpose of each other, or conjugate transpose. So Cholesky factorization is basically LU for symmetric matrices. Right? Square root is related to them, but the idea of square root is technically a little bit different, whereas LU or Cholesky, you know, if you do Cholesky, it's often done as C star equals A. Because if that's a lower, then when you transpose it, you get an upper. Right? The square root is without the star. You technically multiply something by itself to be able to get back to the original. Right? Or anything close to this. So this is technically square root. This is Cholesky, and LU is just, of course, LU equals A. Right? Which you would only do this if it's non. But I would say that you could also do anything else that's pretty close to these. You can approximate them. So a lot of times what people will do is what's called a low rank factorization. So we've talked about this with some other situations. What if you calculated the first couple or the dominant modes of any of these factorizations and you use those, right? Be fairly easy to do an approximation where, just like with the eigenvalues, you grab the biggest ones and the smallest ones and you just kind of approximated the system by that. You know? And we talked about kind of the equivalent with SVD. We could do those low rank factorizations where it does a pretty good approximation of your matrix, just with less terms. So if we used a lower ranked version of A that was small, right, and then just add an identity in so it's invertible, then it would be pretty easy to calculate our inverse and then do some operation off of it. So a lot of times we can do that to correct if there's particularly big or small modes. We can use that to correct them. Right? So any of these type of factorizations, if you can do them quickly, the whole key is you got to be able to do them fast. And if you can't do it fast, you're just spending too much time here. Now, another one that I think is actually kind of fun, relates to a lot of practical engineering problems. A lot of times in engineering, we'll have to use what's called finite element methods. And to get a good solution, you often have to use a very fine grid. Right? I do medical imaging, and a lot of times with medical imaging, to get a good looking image, you need a really fine solution. That adds a lot of work. Well, it turns out, what if I take a very low res image? I'm still going to get some basic features about what's going on. And it's often those basic features that are going to mess you up. So what if I did a low res approximation And I use that low-res approximation to be M. Right? So now I've just got some repeated block values, but I still have the basic structure in it, but it's kind of blocky and chunky. Well, I can still calculate the inverse. It's actually really easy because it's blocky and chunky. It's going to be pretty quick to invert because there's a lot of repeated values that are in there. But that means that since it's kind of blocky and chunky like that, quick to do, good approximation to life though, the fine detail can then build off that basic approximation. So I kind of correct the ugliness at a very kind of rough area, and then I smooth in on it. And so that will also work in a lot of different situations, you know, doing a rough approximation. You can do it as low resolution. For a lot of problems in finite element methods and things, those ones work pretty nicely. Okay, does all this make sense? And I would say this is kind of version 1 when you're doing it. This is the version that's trying to just say, hey, I'm just looking at conditioning these different things. Right? I'm just trying to simplify what's going on here. This is version 2 where you're trying to, you know, maintain the eigenvalues off them. And you have to decide which one applies. Do you apply it to both sides or one? Okay. Now, one other thing that I'd like to mention with this, the book doesn't mention this, they give you several other ones, but this one kind of gives you the flavor of a bunch of them. So I think these are kind of some good archetypes to think about it. If you come up with anything else that roughly is going to lie anywhere in the range between 1 and A's eigenvalues, right? Because that's what we're trying to do in every one of these cases. Because remember, 1 is the identity matrix, which essentially doesn't give me any help on this side. A itself as your M saves you everything here, but makes that every bit as expensive. So that's kind of the two extremes. If you're somewhere between 1 and the actual eigenvalues, somewhere in that middle, it will split the work and often save you a lot of time. So that's kind of what we're doing in every one of these. Try to get somewhere in between. And the closer I am to perfectly in between and clustering them together, the better I am. So we just want to find fast, easy ways to do that. That's the whole trick. All right? Fair? All right. So that's kind of our pull on these. One other fun thing that I mentioned that this is related to is there's a scaling issue that often goes on, and we don't often think about it inside of just the regular AX equals B when you're solving these squares. Right? Like let's say for instance that I'm doing something, let's say I'm going to use Ohm's law, right? What's Ohm's law? Okay, so I've got V equals IR. Now, let's say for instance that I've got a voltmeter and I've got a whole bunch of resistors or other things inside some grid. I can rewrite this thing as a R, which is a matrix now that kind of describes the network of how all these resistances are spread around. And I've got a bunch of currents flowing there that I'd like to know what those currents are, and I take voltage measurements at appropriate node points or whatever, right? So basically Ohm's law. Now, this is basically our AX equals B equation. This is one of those reasons why it turns out that a lot of engineering problems can be written this way. But I can do things like I can rescale my units. What if I measure this in volts, but I want this in milliamps? Right? Is that a problem? No, I just have to appropriately scale the R, right, to be able to handle that. However, in least squares, it changes things. It really gives you a different solution. And I'm pausing a little bit because I want you to think why you think it is. And I'm going to show you exactly why that works in a sec. But take a sec here to try to figure out, why do you think rescaling, so that they're just in different unit breakdowns, shouldn't matter, right? But it does. If you took measurements of things spatially, this is some type of a, description of a physical system, and this is some things I can't measure directly as distances, and this is distances. If all my distances are feet, and I decide to convert them all to meters because I don't want to deal with stupid old archaic systems, right? Shouldn't change things, but it will actually change your errors. Think for a sec why. Precision where? You're right about it has to do with precision, but it's not obvious where the precision loss is happening when you convert, or even which one's better.
I mean, it most makes sense in like going from meters to centimeters, because anytime you're dealing with a computer, if you're shifting that way, you're losing bits.
So believe it or not, if I deal with it all in meters, like if this was distances and this was in meters and this was in meters, and I switched it to centimeters and centimeters, you get almost no change. But if I decided to measure this one in, centimeters, it would change stuff a bit. So here's where it comes in, right? Imagine you draw this problem, and this is my independent one, and this is my dependent one, right? So if you want to think of it, I've got an equation for a line here, and this says y equals mx. Goes through the origin, so b is equal to 0, right? So in our original problem, right, ax equals b, right? Your y-axis, this is your measurements, the b part of our vector equation. And this is the independent ones, the ones you're trying to figure out. You're going backwards. That's actually all we're doing in least squares, right? Now, if I change it so one of my units, I'm measuring thing in feet, but I want my actual observation, the hidden variables in meters, right? When I were to plot that, the slope changes. That's all you're doing. You're just scaling it, right? So if I'm in meters and meters, millimeters, millimeters, it's still going to stay the same exact slope. Right? Now, when you take observations, right, on the original problem, they go around kind of like this. When I rescale them for the new problem, doing meters and feet or something stupid like that, right? When I plot those, they kind of still go around here. But what happens is, when you measure, you're measuring only in the vertical to solve least squares, right? When you've changed the scaling, it's going to asymmetrically stretch the vertical direction, because I've changed this one, but I haven't changed this one. So if you symmetrically deal with them, there's a direct relation to how everything scales nicely. But when you just scale one dimension, it'll throw it off. Does that make sense? Right? It's the difference of, did you make this bigger or smaller? As you get the slope steeper and steeper, the vertical direction is going to increase, so you've lost precision in that sense. Okay? That's where the problem is. And it's well known that least squares is susceptible to this type of a problem. But that also means if you were to change your dimension, right, either way, you could end up getting differences in how they go. So the best thing you can do is to get something nice compromise between the two, which is near slope of 1. Right? Slope of 1 is the best compromise of the two-dimension resolutions you can get. That's actually what we're doing. We're trying to get this equation here to look more and more like all your eigenvalues are clustered around 1. All the slopes are clustered at 1. That's actually what you're trying to do. You're trying to mitigate the slope problem. And by getting it kind of right on that 45, you're getting the best compromise between the two. So if you want to think about it, if I'm here and I'm trying to go back, because that's our thing, we took a measurement and we want to know what the input was. It's the whole problem with solving for x. If I'm off a little bit, the problem is really insensitive over here, right? So your precision is not that great because lots of measurements, no changes. I'm not huge on that, right? And it causes the errors on that to be bigger. But if I'm over here, the reverse is a little change here will cause a big change. I don't like that either. I would really like what's kind of in the middle, right? If you go up, it has the same effect on my output. My variables have about the same amount of precision in them, right? That's the better situation that's on, right? So from just kind of like a measurement standpoint, you really want the accuracy of all your variables kind of ballpark in the same. It wouldn't be really good if GPS was kind of accurate to within an inch or within a couple centimeters in the north-south direction, but like 50 meters or so in the east-west, right? That would not help you. We really want the scales somewhat similar. Does that make sense? That's what you're doing here. So there's a lot of other techniques that are out there that will try to do this. So you might have heard of weighted least squares. Anybody ever heard of weighted least squares? A couple people have, a lot of people haven't. The whole idea with weighted least squares is they take the original problem which is normally in the 2 norm, and they now pick a W norm. But that W norm is not like a number. It's actually a matrix. And what you're solving in this case is AX minus B times W times AX minus B transpose. And you want to minimize that. That's what we mean by that norm. If you take this and Cholesky factorize it, what you end up with is the kind of the equivalent of the square root of this multiplying A and B on the left. That's exactly what you're doing here. And the whole trick to this type of a thing is you're trying to pick W to move them all so they're right on that 45. It's the same exact trick, it's just a preconditioner. Right? So if you look at anything, so there's a lot of ways of how do you pick the weights in weighted least squares. Anything that would let you pick a good weight in weighted least squares will let you pick a good preconditioner. So the book doesn't mention this one, but it is true that you can also do weighted least squares. All right? The weights for weighted least squares will make a nice preconditioner. So I give you these as categories, and like I said, the book has tons more. If you pick for this same type of a goal, and you're just doing symmetric, it works for the eigenvalues. So they give you a bunch of eigenvalue ones, which have their varieties, but you know, it's again for that same basic goal. Does that make sense? All right, so then the question really is, how well does it work? All right. And I figured we'd have a little bit of time when we were done kind of talking the idea behind it. The book has a good example, but they barely worded enough to be able to read it. So what I figured we would do with our time remaining is to have all of you try to code up their example in, I think our last chapter is 39. Anticipating that you may or may not have it. I brought my book. I actually tried to print it out, but my Mac is not happy. And after some failed attempts, I gave up and just grabbed my book. Okay, now I guess it's chapter 40 is the last. Try to get my book to stay open here. Wrong way. Okay. So you'll see down here, this is basically what I have written on the board, right? We usually call m, and when we take the square root of m, or the Cholesky factorization, we usually call that c. So when you're seeing this, this is kind of related to your M matrix. So if you made M pretty close to A, you're doing the symmetric thing. We typically want to try to pick these as near square roots. In our case that we're going to do over here, C is going to be picked to be diagonal. So the difference between C inverse and C inverse transpose is going to be 0. So in our case, this will be C inverse times A times C inverse, and then, C times X, and then C inverse B, because diagonal, right? C will be diagonal, transpose of a diagonal is the same diagonal matrix. Does that make sense? This is the setup that they're looking at doing though. This is going to be your new A, the preconditioned A. This is your preconditioned B. And you will get back from your solution. This is a symmetric matrix, so we're preserving the symmetry here. You're going to get back from it, a Z, which is going to be equal to C star, or in our case, C times X. So you'll have to take that Z to get the true X and multiply by C inverse. Does that make sense? Okay. And you're going to do this using your conjugate gradients algorithm. So it's also a good way to test it. What they do is they pick, and they say they picked it from an earlier problem, I think somewhere a few chapters before. But it's not as important. They're going to pick 1,000 by 1,000 matrix, so fairly decent sized matrix. It's going to have a fairly high sparsity structure. There's going to be kind of a tridiagonal matrix with 2 off diagonals somewhere around 100. Right? So that's the basic structure. The main diagonal is going to be made up of this 0.5 times the square root of I. Right? So that's your main diagonal. That's the II elements of matrix A. And then all the other terms will be equal to 1. So on the sub and super diagonal, right, the first one, there'll be 1s on either side. So you'll have this, your matrix structure will look like that. 0.5 plus square root of I, 0.5 right, plus square root of I. So, and I will be 1 here, 2 here, so on and so forth. Okay, this is the 1, 1, 2, 2. And then you'll have 1s going like that. So that's what they're trying to describe with those, the kind of the first sentence for the sub and super diagonals. Right? And then there's one more thing. When you go all the way down to where I minus j is equal to 100, or j minus I equals 100. So this one, after 100 down or going over 100, it's going to be a whole bunch of ones there also. So the easiest way to do this is just do a bunch of for loops. Right? Do a for loop for the main diagonal, put in all those. Right? And that'll be 1,000 long. Then you could do a for loop 1 to 999, and you could do the first sub and super diagonals. Right? So you'll have, the elements I and I plus 1. And also I plus 1 comma I will both be 1. And then for this last one, there's going to be 900 of them, right? Because they're 100 down. So you could just do a loop for I equals 1 to 900. And then you'll do it for the A, I, comma, I plus 100, and A, I plus 100, comma, I. That'll give you the sub and the supers. And make those equal to 1. Does that make sense? So that'll generate their A matrix. Their B matrix is all ones. So it's 1,000 by 1 matrix, all ones. That's fairly straightforward to do. They give you C, which is going to be equal to the square root of M, and M is just the diagonal. So you ignore all the other terms. So this is another way you can often pick them, is you just ignore everything. You assume that you have a diagonally dominant system, i.e. the diagonal is bigger than anybody else, and you just